In the last section, we alluded to the possibility that we could learn and adapt the classifier during the learning process itself. How could we do that? Well, one way to start with this point is to think about diversifying the data set itself. So we'd like to be able to train a classifier on diverse sets of data, one for each of the different small t classifiers that we might want to individually build and unify them into a single classifier. This is similar to the idea of using a validation set, which is producing a hypothesis based on smaller amount of training data and then validated on held out data. So what can we do? Can we manufacture more data than is observed in our M instances? Sure, we can. Well, not really, sort of. What we're going to do is employ the idea of bootstrapping, which is a statistical tool that resamples from the dataset to simulate other datasets. This is really similar in spirit to the idea of dataset augmentation that we see common in deep learning. For example, in convolutional neural networks for images where we resample parts of the image by cropping, scaling, or inverting. In both cases, we have a single dataset that's being used, and we're manufacturing additional data points from the original dataset. We're going to use the idea of bootstrapping in this notion of bagging. Bagging is an acronym for bootstrap aggregation. The idea has both of these points put together. First, we're going to bootstrap, which means that we're going to sample a new dataset tilde dt, where we resample the same number of m examples from the original dataset, but we're going to do it uniformly with replacement so that we introduce some data randomness. For example, some of the data points will be sampled multiple times and some of them will be left out. That's the bootstrap part. So for each of the t iterations, 1 through t, we're going to request through the bootstrap m-size data examples tilde dt using the bootstrapping process. We're going to then obtain a hypothesis for each of these tilde dt datasets by running the learning algorithm A to output a hypothesis ht. Then, for the aggregation part of the algorithm, we're simply going to take a uniform vote over all of the hypotheses on a particular input example to get out the final hypothesis value. This is a really simple meta-algorithm, which is a uniform voting procedure on top of a base algorithm, so we could use it for any machine learner that we've learned about. Here's an example of the Perceptron learning algorithm that's been bagged. Again, here we have a two-class classification problem which receives two input values, x1 on the x-axis and x2 on the y-axis. We've taken these data points that you've seen here and bagged them into 25 times. So we're resampling all of these points 25 times and creating 25 new data sets with some of these points sampled multiple times and some left out in each of the bags. This results in all of these 25 gray hyperplanes as what the Perceptron learning algorithm did with those particular points. For example, we might have learned this decision boundary in Perceptron learning algorithm by sampling certain points. For example, all of these blue points and all of these red points. In this case, we might be able to come out with the decision boundary as shown there. We allow all 25 of these hyperplanes to vote on the decision boundary, which is shown in black. We can see that this decision boundary is piecewise linear, but illustrates a complex function overall. In this particular case, it gets all of the particular examples in our training data set correct. Because of the way we have bootstrapped our datasets, the resulting bagged algorithm works reasonably well, especially if A is sensitive to data randomness, which we already showed in the case of Perceptron learning algorithm. For a large-size dataset of size M, each of the bootstrapped samples of tilde-dt is expected to have about 63% of the unique examples in the dataset. The remaining 30-odd% are all duplicates. You should try to figure out how the math of this works. Basically, we have M trials which we're trying to sample a data point, and the expression inside the parentheses specifies the likelihood of whether that is a unique or duplicate point. The result is that the model is trained on each iteration with significantly less data, but that the final model itself has seen all of the data points, in fact quite a number of times for large M. This means on average, an example will be in the majority of the bootstrap samples of tilde-dt. Let's illustrate how this works. In the columns here we have the particular hypothesis that we're learning, all the way to the tth one. On the rows we have the particular data instances that are within our data set, all the way up to M. For each instance, some of the classifiers will be exposed to that particular example. For example, it might be present for the learning of H1, H3, and HT, but absent for H2. This is going to be randomly done because we sample a new data set each time for each of the different hypotheses. So we can see that the starred instances within each column are not used for obtaining the particular hypothesis at that particular iteration. And these are called out-of-bag or OOB examples. Of course, we know the number of examples that are OOB. These are the ones that are left out of the bootstrap sample. And we can use these to validate RH that's learned for that hypothesis, somewhat akin to what we do in validation. Our cost function for OOB would just be the average pointwise cost of how well our impoverished classifier does when missing those out-of-bag examples. Since OOB has a very close relation with validation, let's study how they differ. At the top again, we have our out-of-bag example, where basically every column represents a particular bootstrap sample, in which some of the instances are missing, but the majority are present. In validation, we don't do it exactly this way. We cut our dataset into specific portions. So part of our dataset is missing for all of the different runs of individual models. So for example here, instances 2 and 3 are cut out of our training dataset, and we only expose all T classifiers to this for assessing their performance. In fact, we can think of bootstrapping as a reweighting process as well, to affect a weighted vote. Let's say we have a dataset consisting of 4 points, and via bootstrapping to get a new dataset tilde-dt, we have sampled the first point twice, the second point once, omitted the third point, and sampled the fourth point, resulting in the dataset that you see on the bootstrap line. If we care about particular examples in our training data, we might weight them and have a weighted function that uses a particular tuning cost parameter, U, that's associated with individual points, J, and then assign it a different weight. For example, here we might say that instance number 1 is very important and carries twice the weight of a normal example, and instance 3 is noise, and so we would give it a weight of 0. We might be able to determine that based on domain knowledge about what is important to get correct in a classification problem. We can see that bootstrapping does the same thing, but in a random fashion. By sampling the dataset multiple times, we get different weighted versions of the original cost function because we have oversampled some points and omitted some points entirely from the dataset. In this way, we can say the hypothesis set that we're using is diverse also because we are minimizing the bootstrap weighted error, as you can see on the right-hand side. The nice thing about bagging is it reduces variance because we are averaging over many different hypotheses that are trained over different subsets of our data. That's great, but it has little effect on the bias. If we have a complicated model like a decision tree, we are still working with the entire spectrum of script H, our hypothesis space. So that gets us to the question of whether we can use a more simplified algorithm for learning in the case of ensembles. We're going to investigate that next.